Down there, life continues. The traffic is awful, stocks go on trading, and Star Trek is still showing.
morning, grade 9 learners, and welcome to our today's natural sciences lesson. My name is Mr. Moses Mutwahai, and this lesson is proudly brought to you by the Gauteng Department of Education and the Pakama Research and Development. Welcome to our lesson. Guess what? For today, we're gonna learn about non-contact forces, which we also call field forces. Okay, so before we get into our lesson, let's start with our first question. Do you know what is a force? When I'm talking about force, do you know what I'm referring to? While you're thinking about it, let's get deeper into non-contact forces. So our lesson objectives, they go as they follow. Meaning after this lesson, I want you to be able to do the following, all right? Define a force, identify the unit of measurement of force, calculate for force and weight, and also name and describe the non-contact forces. All our objectives, we find them on our CAPS document, page 71 to page 72. All right, so moving right along, your pre-knowledge. So when we talk about forces, if you go back to grade 7, you will remember you learned about the gravitational force. And if you go back also to grade 7, you did gravity. And in grade 5, we learned about energy and movement. What about grade 8? In grade 8, we learn about static electricity. So if you look at all those pre-knowledge, those are things that you learned before, so we're gonna apply them today as we dig into non-contact forces. So our terminology goes like this. What is a force? So we are answering the first question that we asked when we started with our lesson. A force is an action that can be described as a push or a pull, all right? Or twist of an object. And then we have a Newton. What do you know about a Newton? A Newton is a unit of force, all right? And then a contact force. So when we talk about a contact force, we are simply referring to a force that is being exerted when two objects touch each other, right? So whenever there is touching and contact, that's what we call contact forces. Okay, are we good so far? Moving right along, a field force. What do you know about a field force? Okay, a field force is a force that is exerted over a distance, right? That is exerted over a distance, also called what? A non-contact force. So this force, it takes place through space, right? Wherever there is no contact between what? Between two objects. Still continue with our terminologies. Non-contact force, which is our main topic for today. What do we know about non-contact forces? How can we define them or how can we describe them? We simply say a non-contact force is a force that is exerted over a distance. It is also called a field force. So if you don't want to say a field force, you can call it non-contact force. If you don't want to say non-contact force, you can also refer to it as field force. Are we good so far? Moving right along, gravitational force, right? Gravitational force, pulling force that bodies exert on each other over a distance due to their masses, all right? That is what, so gravitational force is a pull force that is exerted between two objects due to their masses. And then magnetic force. So when we talk about magnetic force, right? So we're referring to magnet. So a magnetic force is a force that two magnetic materials exert on each other over a distance. So when you put a magnet and a coin, whenever the coin is being pushed or is pulled by the magnet, that's what we call a magnetic force. And lastly, what do you know about the electrostatic force? Electrostatic force is a field force that arises through differences in the electric charges of objects. So for there to be electrostatic forces, the objects need to be charged. Are we good now with our terminologies? So if you can take back step to our terminologies, we defined a force, we defined a contact force, we defined a field force and a non-contact force. We also spoke about gravitational force, magnetic force, and electrostatic force, and not forgetting newtons, the unit of measurement of force. Are you good? Moving right along into our non-contact forces, the baseline test, right? So, if you remember last week, you learned about contact forces, right? Last week, you learned about contact forces. So, did you really understand what happened last week? Let's check our understanding throughout our baseline assessment. It goes like this. Number one on our baseline, define a force. Number two, list two main types of forces. List two main types of forces. And number three, list three examples of contact forces. Three examples of contact forces. So, we have three questions. We'll take 3 minutes to complete our baseline assessment, and then we go into our non-contact forces. So 3 minutes to complete the baseline, and then we proceed with our lesson. Oh yes, today we are posting things, right? we are doing non-contact forces. So if you don't understand anything about forces, or you have questions, or you have answers, send them through on our WhatsApp number on the screen, right? Engage with me. Let's talk to one another. Non-contact force. Okay, going back to our baseline assessment. Number one, define the force. Number two, list two main types of forces. And number three, list three examples of contact forces. Let's check our answers. Make sure you mark in your work, all right? Okay, so our answers go like this. Number one, a force is a push or pull, right? Also, you can say what? A force is an influence that can change the motion of an object, all right? So, we've defined a force. If you wrote is a push or pull, that's a mark, right? If you had a different definition, for instance, you said that a force is an influence that can change the motion of an object, is also correct, okay? And then for number two, we are supposed to name two types or two main types of forces, which are, can you guess? Contact forces and non-contact forces, which we call the field forces. And then for number three, we're supposed to list three examples of contact forces. Can you guess them? Yes, keep them coming, keep them coming. Anyone to guess? To give it a try. Moving right along. Examples of non-contact forces. Tension. You have tension? Torsion. We have torsion also. We have also compression. And also we have what? Shear force. And lastly we have what? Friction or frictional force. So, tension, torsion, compression, shear, and friction, those are examples of contact forces. Hope you got them correct. If you got them wrong, fix your mistakes. Now you know the difference between, or you know the examples of contact forces. So, we get into our non-contact forces. What is a force? So look at our pictures there, right? They show you an illustration of what is a force. If you look at picture 1, picture 2, picture 3, they all show you that a force is a push or a pull. Alright? First, a push or pull that causes an object to move, stop, or change direction. And then, in physics, a force is anything that makes an object to accelerate. And lastly, if an object is stationary, so when we say an object is stationary, we mean it is at a rest position. It is not moving at that moment, right? So if you look at me now here, I'm stationary, right? So we are saying if an object is stationary, it will need a force to make it move, right? So here's the object. It's stationary. If you apply a push force, it keeps on moving. All right. So how do we measure a force, right? So the SI unit for force, they are always newtons, right? Capital letter N, Newton. 1 Newton is a force, right? We use a spring scale to measure a force. There is our spring scale that we use to measure a force. So a force is measured in newtons, okay? Whenever you think about newtons, is a unit measurement of force. Non-contact forces, our main meal for today, right? We're gonna dig into non-contact forces. So let's get this straight. I want you to understand, right? And to be able to explain when you get home, you should be able to explain to your friends, to your family, to say, you know what? Today we learned about non-contact forces. This is an example of a non-contact forces. It takes place in this way. Let's check them out. Non-contact forces produce their effect through space, meaning the force can take place without the objects touching one another, or the force can be experienced without the contact between two forces. Simple terms, non-contact forces produce their effect through space, right? Without the objects touching each other. They are also called field forces. Examples: gravitational force, magnetic force, and electrostatic force. Can you remember them? Examples of non-contact force: gravitational force, magnetic force, and electrostatic force. So let's look at an example which shows how non-contact force they act, or how they act through space. So look there on our diagram, there on our picture. We have a ball of magnet there, and we have small pieces of what? Of metal. So as the ball is placed in the same region as those pieces of magnet which are magnetic, they are easily attracted, right? They are easily attracted towards the magnet. So you see that force already between the two objects. There was a force of what? Of attraction. The magnetic metals or material, they were attracted to a magnet, and therefore they follow the magnet. That's what we call the force of attraction, right? When we say that unlike, they attract. Moving right along, gravitational force, which is our first examples of non-contact force. So what do we know about the gravitational force? Some they call it the force of gravity. All right, force. So a gravitational force is a force that acts between two masses, right? It acts between two masses. The force between the Earth and the Moon is also considered the gravitational force. The Earth also has the gravitational pull on all objects on its surface, close to its surface, all right? And the force of gravity, or the gravitational force, it is called an attractive force. Why? Because it pulls every object towards the center of the Earth. Are we good so far? Are you getting this gravitational force? Let's get deeper into it. It's also called the Earth gravity. It acts downwards, right? Downwards towards the center of the Earth, right? So, as you are climbing a tree, or you're on a mountain, or you're hiking, as you're about to fall, the force of gravity, the gravitational force, is the one that says, come down, come to me. So you go down towards the center of the Earth. Do we understand the gravitational force so far? It's a force of gravity that acts downwards towards the center of the Earth. It's the force that is experienced between two masses. Still under gravity, let's look at it. You see an example there. There is our teacher, as he was reading a book under the tree. The apple just fell on top of his head. So what made the apple to fall straight like that? Because now you look at it, between the earth's surface and the apple, the position of an apple on a tree, there's what? Space there, right? However, the gravity is able to pull the apple downward to the center of earth. So that type of force is depending. However, two forces, there is space between them. So that's what we talk about, non-contact forces. Moving right along, gravitational force. We still under gravitational force. Gravity causes object to accelerate downwards, right? So every time gravity, you always go down, come down, come down. So whenever objects are falling downwards, that is because of the force of gravity, or the gravitational force. Air resistance. What are we referring to whenever we talk about air resistance? Do you know what is air resistance? Or sometimes you call it air friction. All right. Air resistance, fluid friction, acts in an opposite direction, right? Due to the motion, and reduces acceleration. So as you are falling downwards, the air resistance is going upwards. It's always opposing what? It is always opposing the force of gravity. So air resistance is acting upwards, and the force of gravity is acting towards the center of the air. There is it. So let's take, for example, two friends, they go on a skydiving. The other one is a parachute, the other one doesn't have a parachute, right? They both jump out of the plane, shoot, they jump out. The one with the parachute, boom, lands on the parachute, and now he's able what? He's able to sustain his movement in the air. And the one without a parachute, what's gonna happen to him when he jumps off the plane? He's going straight downwards. Why? Because the force of gravity is calling him to say, hey, come down, come down. And he's gonna go at a higher speed, right? At a higher speed, except for the one with the parachute. Why? Because with the parachute, now it's open above now. So the air is pulling you upwards and the gravity is pulling you downwards. So the two forces, which is air resistance or friction and gravity, they act in opposite directions. So it will take time for the guy with the parachute to land on the Earth's surface. Unlike the one without a parachute who just went to dive in, he will get there faster and he will be hurt because the damage will be hard. The impact will be hard because the speed that is coming down with is much greater than the one with a parachute. Why with the parachute? Because the parachute, the air resistance is opposing gravity. So by the time he lands, he will land slowly and the impact will be less. There you see, that's me with my parachute there, right? So as I'm gonna land smoothly. But if I don't have a parachute, I will get hurt. Moving right along, the impact of gravitational force. We're still under gravity. I want you to understand this gravitational force perfectly. Gravitational force has the effect of causing any falling objects to build up speed, right? So as you are falling downwards, you are building speed. In the absence of air resistance, object accelerates towards the center of the Earth at the rate of 9.8 meters per second squared. So this one, pay attention to it, right? This is the constant, right? Constant value of the gravitational acceleration on Earth. Please, on Earth, right? On Earth, our constant gravitational acceleration is equivalent to 9.8 meters per second squared. All right, so that's a constant value. Don't change it on Earth. The longer the object remains falling, the greater will be its final speed when it hits the ground. This is called gravitational acceleration, which is represented by letter G, right? The small letter G. So you will see how we're gonna use our constant value when we are doing the calculations. The relationship between mass and weight. So whenever we talk about the gravitational force, we always gonna mention mass, we always gonna mention weight. Okay, so we want to know the relationship between mass and weight. Those two, how are they related? Do you know how they are related? Can you tell us how mass and weight are related? Let's find out. Okay, weight is a force of gravity with which the earth attracts or pulls down an object, right? So weight is a force of gravity which pulls down the object. Mass, however, mass is the amount of matter that a substance or an object consists of, right? So a mass is the amount of matter that a substance or object consists of. It is the heaviness of an object. The weight of an object is proportional to its mass. The greater the mass, the greater the weight, right? The greater the mass, the greater the weight. So, how do we calculate for weight? Because in this topic, we're gonna find the calculations of weight. And then how do we calculate for weight? Alright, we remember that we learned that the weight is a force of gravity which acts on objects, pulling them downwards, right? And the mass is the amount of matter that an object or a substance consists of. So then, how do we calculate weight? So whenever we calculate weight, we simply say weight is equals to mass multiplied by gravitational acceleration, where W, it represents weight, right? Which is measured in newtons. Because weight is a force. And when we started our lesson, we say newtons is a unit measurement of force. Therefore, whenever we calculate weight, our answers will have the SI unit of newtons, the capital letter N. What about M? What does M represent? Can you give it a try? What does M represent? Can you guess? Yes, M is for mass, right? So the M is for mass, which we measure in kilograms, in kgs, kilogram. Don't forget that. And what about G? What is G? What is G? Well, G is our gravitational acceleration, which is the constant value of 9,8 meters per second squared. So there it is. So every time you calculate for weight, this is the formula that you're going to use. Weight is equal to mass multiplied by gravity. So let's look at our example. Let's do example 1 to see that we can calculate this weight. Example 1. Calculate the weight of a person who has the mass of 120 kilograms on Earth. On Earth. You see, I'm being specific, on Earth. So, how do we do this one? So, remember, my science learners, every time you do your calculations, have data, all right? Have data. Be online. So, what's our data? We get our data from the statement or from the question that is given. So, if you look at our question, we talk about weight, we talk about mass, we talk about Earth. So that means we can compose a data there. So here's our data. The mass of our person is 120 kilograms, right? And the gravitational acceleration on Earth is equivalent to 9,8 meters per second squared. But do we know the weight of our person? We don't know that the weight, right? We don't know. But I taught you now how to calculate weight. Can you remind me of the formula? Can you remind me of the formula? Yes. Weight is equivalent to mass multiplied by gravitational acceleration, right? So there is our formula. So every time you do your calculations, make sure you have a formula, right? You have a formula. It guides you, right, to see what you are looking for. So now, W, which is weight, is our subject of the formula. And if you go to our data, it has a question mark. We don't know our weight. That's what we are looking for. Okay, so weight is equal to mass multiplied by gravity, where we say 120. Where did I get the 120? From our data is the mass of our person here, right? There's the 120 coming from. I got it from here also, all right? And then, because we said on Earth, and then our gravitational acceleration on Earth is 9,8 meters per second squared. So, do it there with your calculator. Say 120 multiply. So, whenever you see these brackets, the brackets, they represent what? Multiplication. So, we say 120 kilograms of the man multiplied by 9,8 gravitational of the man on Earth, which is equivalent to 1,176 newtons. That is for example 1. Did you get it? Were you gonna get it? Were you following the plot? Are we on the same boat? Remember, I want you and I to sail together. Alright? If you don't understand, come to the light. Send those questions on our WhatsApp number on the screen, and then we can be able to help you to come to a proper non-contact force understanding. Moving right along, how to calculate mass now. Now remember, the first example we're calculating weight. Now the second example, we are calculating mass. How do we calculate mass? Can you give it a try? Can you calculate mass from the formula that we just did now? Let's give it a try, right? Remember, if we do this together, it's gonna be easy for you to understand how to calculate weight, to understand how to explain non-contact forces and name the examples of non-contact forces. Example 2. Calculate the mass of a packet of sugar That is a weight of 78.4 newtons. Okay, so data. Always have data. It is important to have data, right? So that when you do your calculations, you see which ones are your known variables and which one are your unknown variables. Moving on along, our data goes like, do we know the mass of this sugar? We don't know the mass of that sugar. Do we know the gravitational acceleration on Earth? Yes, 9.8 meters per second squared. Do we know the weight of that sugar? Yes, 78.4 newtons. So to calculate, we're gonna use our formula where we say weight is equal to mass multiplied by gravity, but here we are looking for mass. So let's substitute our values. Our weight, 78.4, alright? And the mass, we don't know it. Question mark, right? So it remains letter M. And the gravitational acceleration on Earth, 9.8. So 78.4 is equal to 9.8 multiplied by M. What do we get? Yes. Yes, I can see some of you now. They're lost now. 9.8 multiplied by M. What do we get? We get 78.4 is equal to 9.8 M. Alright? But we are looking for M, right? Remember, we are looking for M. M is our friend who's missing. That's who we are looking for. How do we solve this? We want the mass of this packet of sugar. So how do we go to the next step here? How should I resolve this? Anyone to help us? Oh, yes, right? So we're gonna divide, right? We're gonna divide both sides by 9.8, right? So we're gonna say 9.8 m divided by 9.8. So this one divided by this one, it's 1, right? They cancel each other. 1 multiplied by m is m, all right? Or 1m, okay? So 78.4 divided by 9.8 is equivalent to 8 kilograms. 8 kilograms, kgs. So if you look at the answer for example 1 and the answer for example 2, they are different, right? Example 1, we are looking for weight, right? That's why our answer had what? Newtons. And then example 2, we were looking for mass. That's why our answer is measured in kilograms. Are we good so far? Are you getting this weight and this mass? Let's move on then. So, what about the gravitational force in space, right? In space. Because if you pay attention, whenever people go to space, they float, right? They float. You'll never see them walking on the ground, right? They float. Why are they floating there? What's happening there? The gravitational force that exists between the Earth and the Moon keeps the Moon in orbit around the Earth, alright? So the pull between the Earth and the Moon causes tides by the Moon exerting a pulling force to the or on the oceans. The motion of all objects in the universe are governed by gravity, right? So in the universe, all the motion is controlled by gravity, okay? Whereby on the Moon, now, remember we said on Earth, we have the constant gravitational acceleration of 9.8 meters per second squared. What about on the Moon? It has changed now. Now it is 1.6 meters per second squared on the Moon, right? So on the Moon, whenever we substitute, the value of the gravitational acceleration is 1.6 meters per second squared. Don't forget, on Earth, 9.8. On the Moon, 1.6. So how do we calculate weight on the Moon then? That is our example 3. Calculate the weight of the man who has the mass of 120 kilograms on the Moon. So, if you are paying attention, you will realize that example 1 has the same values as example 3. But the difference now, example 3, we are on the Moon. So you will see why at the end we're going to have 2 different answers. Our data. I keep on reminding you, have data, be online, okay? So, the mass of the man, 120 kilograms. The gravitational acceleration on the Moon, 1.6 meters per second squared. And the weight of the man on the moon, we don't know. That's what we are looking for. Let's get that weight. Weight is equivalent to mass multiplied by gravity, where the mass of the man is 120 kilograms and the gravity on the moon is 1,6. So 120 multiplied. Remember we said whenever you see brackets, you must multiply. 120 multiplied by 1,6 is equivalent to 192 newtons. So the weight of the man on the moon is 192 newtons. Are we good? That was nice, right? Okay, did you understand? Let's see with our activity 1. Activity 1, okay, fill in the empty spaces. Fill in the empty spaces. So, on activity 1, we have a table. At the top it says place. Where? On Earth, on the moon, planet Jupiter, and on the farm. Object, we have the man, we have a woman, we have an alien, and we have a goat. Okay, and each has a different mass. If you look at the man has the same mass as the woman and the alien, but we don't know the mass of the goat. Do we know the value of G? Do you know the weight? So that is your responsibility to do now. So for activity 1, you're gonna fill in the missing information below. So we're gonna take 3 minutes, right? 3 minutes to complete activity 1, and then we move on. 3 minutes. How do you find activity 1? Is it challenging, tricky, or easy? All right, so look at it. For the first one there, Earth, right? We look at Earth. So on Earth, we say we have a man, right? who has the mass of 65 kilograms. Do you know the value of G, of the gravitational force or acceleration on Earth? Yes, it's what? It's 9,8. So how do we get the weight of the man? So you say 65, right? This 65 multiplied by 9,8. So you get your answer as 637 newtons. Okay, and now let's go to the moon. On the moon, we have the woman who has the mass of 65 kilograms. Do we know the value of G on the moon? Yes, you got it right. Yes, I see those answers are coming through. Please send them through on our WhatsApp, on the WhatsApp number on the screen. The value of G on the moon, 1,6. Absolutely correct. So let's go to Jupiter. In Jupiter, we have an alien which has a mass of 65 kilograms. All right. The value of G in Jupiter, 24,9. How do you get the weight? So you're simply gonna say what? 65 multiplied by 24,9, and then you get your weight as 1,618,5, right? And then what about the gold, right? The gold. So the mass of the gold, how did you get that one? But the goat, where is it? Is it on a farm, right? On a farm. So on a farm, it's definitely, guess what? Has the gravitational acceleration of 9,8. So to get the mass, we got it as 35 kilograms. That was for activity 1, right? So activity 1, it concludes on gravitational force. So now, we jumping straight into magnetic force, right? Now we are attracting, we are repelling. Okay, magnetic force, magnetism. Magnetic force is a force of attraction or repulsion. Okay, that acts at a distance. It is due to a magnetic field, right? So it's due to magnetic field. A magnet. So what is a magnet? Do you know what is a magnet? Have you seen a magnet? A magnet is an object that exhibits a magnetic field and will attract ferromagnetic materials. So now we are talking about magnetic materials and non-magnetic materials. Do you know the difference? Do you know the difference between a magnetic material and a non-magnetic material? Well, metals such as iron, cobalt, and nickel are naturally magnetic, right? So that means if you place that metal next to a magnet, the metal will be attracted to the magnet. The iron will be attracted to the magnet. The cobalt will be attracted to the magnet, as well as the nickel. Some man-made materials, such as steel, are also magnetic. This is because steel contains iron. However, aluminum and copper are non-magnetic materials. An electric current has also magnetic field around it. So here we talked about magnetic force, and we talked about a magnet, and we talked about magnetic materials and non-magnetic materials. Still under magnetic force. Magnetic force. So when you talk about magnetic force, obviously there's gonna be a magnetic field, right? So the magnetic field of an object can create a magnetic force on other objects with magnetic fields. The force is what we call magnetism, right? So magnetism is the force. So unlike gravitational force, magnetic forces are not always pulling forces. So what is the difference between a magnetic force and a gravitational force? A gravitational force is a pull force. It will always pull you downwards to the center of the earth. However, a magnetic force, it exists in both pulling and pushing. So a magnetic force is a force of attraction and repulsion. Okay, a force of attraction is a pulling force that two objects exert on each other. So when they come to each other, that is what? Force of attraction, right? So what about when they go against each other? When they separate or they move away from one another, that's what we call repulsion. They are repelling. They are repelling. A force of repulsion is a pushing force that two objects exert on each other. So when they don't want each other, that is what? Repulsion. So look at them. This is an example of repulsion. So look here, right? These two magnet bars, they're trying to combine them or to meet them together. But as you can see, as you push the other magnet, the other one keeps on running away. No, I don't want you. I don't want you. Can you see there? There's what? Force of repulsion. Because why? Because whenever we talk about magnetic forces, they're like, right? They're like poles. They're like poles. So now we're going to talk about the North Pole and the South Pole. They're like poles. As you can see here, we have red and red. They are the same. So their light will always repel. They will move away from each other. And the unlike, they will attract. Come to me. Come. Alright, so magnetic poles, right? So magnets have two poles called the North Pole and the South Pole, right? Remember, North and South. The magnetic poles or the magnets have two poles, North Pole, South Pole. So the red one, North Pole, the blue one, South Pole. Two magnets will be attracted by their opposite sides. Each will repel like pole of the other magnet. What do we mean by that? We are simply saying the like poles. So north and north, they will repel. South and south, they will repel, right? So the like poles, they repel. And the unlike poles, they attract. So north and south, they will attract, right? They will come together. They will attract each other. Let's see there it is. Opposite poles attract. Same poles repel. So pay attention here. Opposite, right? So we have north and south. They come together, you see? And then down there, same poles here. If you say same poles repel. North and north, they repel. South and south, they repel. They don't come together, right? So you see these two, they come together. This one, they go apart. So always remember, in the magnetic poles, the like poles, the same poles, they will repel. And the unlike, or the different poles, they will attract. Magnetic field is a region around a magnetic material or a moving electric charge within which the force of magnetism acts. So, whenever they say draw a diagram of a magnetic field, this is what we are referring to, right? So, this is an example or is a diagram that illustrates the magnetic field. So, it shows you here that the magnetic field lines, they move from the North Pole to the South Pole. North out, south in, right? So they move from north to south. So always remember, north out, south we are in, right? South the field lines are coming inside. Magnetic field, we talk about the magnetic field lines. Okay, indicate the strength of the magnetic field. So the magnetic field lines, they indicate the strength of the magnetic field. The closer the field lines, the stronger the magnetic force, right? So the closer the field lines, the stronger the magnetic field. Get further apart as they move from the magnet, indicate or it shows the decrease in the strength of the field with distance from the magnet. So whenever there's distance, now they become weak, not strong enough. Indicate, so the magnetic field lines, they show us the direction. So if you look at that diagram or that picture, there were arrows, right? When we said north, we're going out. South, we are coming in. So they move from the North Pole to the South Pole. So they indicate what? Direction. Never cross, right? So the magnetic field lines, they will never cross one another. They will never cross one another, right? They will never cross one another. Let's go to activity 2. Activity 2, just for you, right? So, complete the table below. We have different types of material. We have wood, iron, plastic, aluminum, steel, and paper. Alright, so we want to know which material is magnetic and which one is not magnetic. So if you think wood is magnetic, you'll write wood. Magnetic, you'll write yes. If it's not magnetic, you'll write no. All right. So let's take 2 minutes, right? 2 minutes to complete activity 2, and then we move on with our non-contact forces. So activity 2, we have what? Wood, iron, plastic, aluminum, steel, and paper. Alright, so for wood, is it magnetic or not? No! Wood is not magnetic, alright? So wood is not magnetic. What about iron? Absolutely magnetic. Give it a tick, right? If you got it correct, give it a tick. You got it wrong, fix your mistakes, right? Okay, I can see we have different questions now coming on the WhatsApp. People are worried about aluminium now. Yes, we'll come to aluminium. That is the most interesting part. Plastic, magnetic or not magnetic? No, plastic is not magnetic. What about aluminium? Yes, aluminum is a metal, right? It's a metal. Is it magnetic? Nope. Aluminum, not magnetic. If you wrote yes, mark it wrong and fix your answer. Still, magnetic, yes. And paper. Paper is definitely not magnetic, right? It's not magnetic. So activity 2, that was the conclusion of what? Magnetic force. So guess where we're going? Electrostatic force. What do you know about the electrostatic force? An electrostatic force is a force that two electrical charged particles exert on each other over a distance. Right? So for there to be electrostatic force, they should be charged. Right? The particles or the objects should be charged. They should be charged. Okay. Electrostatic force act in an electrostatic field. An electrostatic field exists around any charged object. Are you charged? So now remember, sometimes when you touch your friend, right, or when you become in close contact with them, you feel that spark. Hey, you see that spark there? That is an example of what? Electrostatic force, because two particles are charged. Another example of electrostatic force is when you comb your hair, or if you take a piece of ruler and rub it on your hair and then put it on top of small piece of paper, you will see the piece of paper will be attracted to the ruler, right? Ruler, so they will jump towards the ruler. Why does that happen? Why? Tell us. Okay. Electrostatic force. How objects become charged. An atom has a small nucleus with a cloud of electrons spinning around. So electrons are negatively charged particles, right? And the nucleus have positive charged nucleus or protons, right? So the positively charged particles, we call them the protons. And then we have the neutral or the neutrons. Which ones? They don't have a charge, those ones. They are neither positive, they are neither negative. They are just in between, right? So we have electrons, which are negative, we have protons, which are positive, and we have neutrons, which are just neutral. They don't have a charge. Okay, so the protons and the neutrons in the nucleus are held together by extremely strong nuclear forces. An atom is electrically neutral. Okay, so still, how do objects become charged? Yes, the number of protons equals the number of electrons. Electrons can be removed, so electrons, they can move around easily, right? Because why? They are outside the nucleus. As for protons and neutrons, they are inside the nucleus held by a structure, right? However, electrons, they are on the outer side of the nucleus. Alright, that's why it's easy for them to move. So NP, note please, protons and neutrons cannot be easily moved. Thus, only electrons are involved in generating static electricity. Okay, so activity 3, we conclude about electrostatic force. So what did we learn about electrostatic force? A learner combs her hair, right? She's about to go to school. When she's done, some of the hair tend to stand up straight, right? So she was doing combing the hair. Refer to the transfer of electrons. Explain how the comb becomes negatively charged when it rubs against the hair. Number 1.2. What is the charge on the hair after the comb is removed? And 1.3. Why does the hair tend to stand up and move away from each other? Let's try to answer that one. All right. So activity 3, let's do it together. Okay. So for 1.1, to answer it, electrons, they move from the hair to the comb, right? So as you're combing your hair, electrons are transferred from the hair into what? Into the comb, right? So now the comb becomes what? It becomes negatively charged. Why? Because it has electrons. 1.2, the hair, it turns upwards because now it's positively charged, right? And now 1.3, since the hair has a positive charge, the hair follicles, they move away from each other. Why? Because they repel. Because according to electrostatic force, like charges will always repel, and unlike charges, meaning positive and negative, they will attract. Those are unlike. But the like charges, which is positive and positive, they will repel. That's why after combing your hair, the hair follicles, they move away from each other because they are all positively charged. And that comb, if you place it on top of a paper or small piece of paper, they will jump towards the comb because the comb is negatively charged and the piece of paper are positively charged, so they attract one another. So that's what we learned about electrostatic force, gravitational force, and magnetic force. So how do we conclude our lesson? The summary. Non-contact forces. Do you remember the non-contact forces? Yes, the type of force that exert on each other without contact, right? Without touching one another. A non-contact force is a type of force that exists between two objects through space, right? Whenever there is no contact. Do you remember the examples of non-contact force? Can you remind us as we are concluding? Yes, gravitational force, right? So gravitational force, which is a force that acts between two masses. What else is a non-contact force? Can you give it a try? Yes, magnetic force, right? So a magnetic force is a force of attraction or repulsion that acts over a distance. Like poles repel and unlike poles attract. North and north, they repel. North and south, they attract. And lastly, we have what? Electrostatic force, right? Which we say that electrostatic force is a force that two electrically charged objects exert on each other. So we learn about non-contact force, we know the gravitational force, we know the magnetic force, and also we know the electrostatic force. So that's where we conclude our lesson for today. Alright, so till we meet again, please take good care of yourself, right? Always sanitize, do your homework, right? And till we meet again, I guess this is goodbye.